For spacecraft designed to operate for decades, this gradual exposure must be carefully considered. For journeys lasting centuries, it becomes an even greater concern. Temperature is another aspect of interstellar space that is easy to misunderstand. It is often said that space is cold, and that is true in a certain sense. Far from stars, there is very little radiation to warm objects, and the background temperature of the universe is only a few degrees above absolute zero. But temperature in a vacuum does not behave like temperature in air or water. A spacecraft does not instantly freeze, because there is no medium to carry heat away rapidly. Instead, it slowly radiates its heat into space, cooling over time. Managing temperature becomes a delicate balancing act. Electronics and instruments generate heat, but without an atmosphere to conduct it away, that heat must be radiated through carefully designed surfaces. Too much cooling and components may fail. Too little, and overheating becomes a risk. Over long journeys, maintaining this balance requires systems that function reliably for far longer than most machines on Earth are expected to operate. Then there is the matter of navigation, which becomes increasingly difficult as distance from the Sun grows. Within the inner solar system, spacecraft can determine their position by tracking signals from Earth, observing the positions of planets, and using the Sun as a bright reference point. In interstellar space, the Sun becomes just another star, and the planets are far too faint to serve as landmarks. Navigation must rely on distant stars and extremely precise measurements of motion, often using instruments that detect tiny shifts in the positions of stars as the spacecraft moves. These methods are effective, but they require time, careful calibration, and functioning equipment. Over very long periods, maintaining that precision becomes more challenging. Communication, too, grows more difficult. Radio signals weaken with distance, spreading out as they travel. The power required to transmit a detectable signal increases, and the time required for messages to travel back and forth becomes longer and longer. At interstellar distances, a message may take years to reach Earth, and any reply would take years more to return. This delay changes the nature of communication. Instructions cannot be sent and carried out in real time. Decisions must be made autonomously by onboard systems designed to handle situations that engineers could not anticipate decades earlier. The spacecraft, in a sense, becomes independent, continuing its mission without the close guidance that is possible within the solar system. There is also a quieter aspect of interstellar space that is not often discussed, because it is less tangible than radiation or dust. It is the absence of resources. Within the solar system, a spacecraft can, in principle, use planetary gravity for navigation, observe familiar celestial bodies, and rely on a well-understood environment shaped by the Sun. In interstellar space, there are no nearby planets, no gravitational assists, no opportunities to refuel or repair. Everything a spacecraft needs must be carried from the beginning, and everything that breaks must remain broken. Over time, small failures accumulate. A sensor stops working. A communication antenna loses efficiency. A power system declines. None of these failures may end the mission immediately, but together they gradually reduce the spacecraft's capabilities. This slow attrition is one of the reasons why interstellar travel, especially journeys involving return, is so challenging. A round trip would require systems capable of functioning reliably for centuries, perhaps millennia, in an environment where repair and resupply are impossible. Interstellar space is also shaped by magnetic fields, faint but widespread, threading through the galaxy and interacting with charged particles. These fields are not strong enough to deflect a spacecraft significantly over short periods, but over very long times they can influence the motion of charged particles and subtly affect the environment through which the spacecraft travels. Another factor to consider is the relative motion of the spacecraft and the interstellar medium. Even at modest interstellar speeds, the spacecraft effectively experiences a continuous stream of particles impacting its forward surfaces. The faster it travels, the greater the energy of those impacts, and the more demanding the shielding requirements become. For spacecraft travelling at a significant fraction of the speed of light, this becomes a major engineering challenge because even tiny particles can carry enough energy to cause serious damage. While current spacecraft travel far more slowly, the principle remains the same. Interstellar space may be sparse, but it is not inert. All of these factors contribute to the sense that interstellar space is not hostile in a dramatic way, but unforgiving in a quiet, persistent manner. There are no storms or explosions waiting in the darkness, no sudden hazards that can be easily avoided. Instead, there is a steady accumulation of tiny effects, each insignificant on its own, but together shaping the fate of anything that travels there. This environment also changes how we think about distance. Within the solar system, distances are often measured in astronomical units, and travel times are measured in months or years. In interstellar space, distances are measured in light years, and travel times at current spacecraft speeds are measured in tens of thousands of years. A journey of that duration is not something that can be planned in the usual sense. It extends far beyond the lifespan of any individual or even any civilization as we know it. A spacecraft travelling between stars becomes less like a vehicle and more like a drifting artifact, carrying with it the faint traces of the time and place where it was built. And this brings us back, gently, to the idea of a one-way trip. Leaving the solar system is not just a matter of reaching escape velocity or crossing a distant boundary. It is a commitment to a journey through an environment where returning becomes harder with every passing year, not only because of distance, but because of the gradual wear on systems, the decline of power sources, and the growing separation from everything familiar. At first, the idea of travelling somewhere and then returning feels symmetrical. You go out, you turn around, you come back. That pattern is so familiar in everyday life that it feels almost like a law of nature. Walk down a road, and the same road leads home. Sail across a lake, and the shoreline you left remains behind you, waiting. Even aircraft that circle the globe eventually return to the place where they began, guided by fuel calculations and navigation systems that assume the journey outward and the journey back are roughly equal challenges. Space does not follow that pattern so neatly. The farther you travel from the sun, the more energy you must spend not only to return, but to undo everything that made the outward journey possible in the first place. This is what can be thought of as energy debt, a quiet but unavoidable consequence of motion in a gravitational system. To understand this, it helps to think again about the image of a valley, the one formed by gravity. Leaving the solar system is like climbing out of that valley. You begin near the bottom, deep in the gravitational pull of the sun, and you expend energy to climb upward, gaining altitude in a landscape that is invisible but very real in its effects. If you climb high enough, you reach a point where gravity no longer has the strength to pull you back. You're free to drift outward indefinitely. But imagine now that you want to return. From that high altitude, you must descend back into the valley, which gravity will help you do, but descending alone is not enough. If you fall freely, you will accelerate, gaining speed as you approach the sun, just as a falling object accelerates toward the Earth. By the time you reach the inner solar system, you would be moving far too fast to stop or to enter orbit around any planet. To return safely, you would need to slow down, shedding all the energy you gained while falling inward. And that is where the true cost of returning becomes clear. Every bit of speed gained during departure must eventually be cancelled. Every kilometre per second of velocity requires fuel to remove, just as it required fuel or gravitational assist to create in the first place. This is very different from travel on Earth, where friction and air resistance naturally slow moving objects. A car coasts to a stop when the engine is turned off because the road and the air absorb its energy. In space, there is no such help. Motion continues unless something actively changes it. A spacecraft must carry the means of slowing itself down, and that means carrying fuel. Fuel, as we have already seen, is heavy. Carrying enough fuel to decelerate after a long interstellar journey would require launching far more fuel at the beginning, which in turn would require larger rockets, more fuel to lift that fuel, and so on. The requirements multiply quickly, turning the idea of a round trip into a problem of staggering proportions. There is another subtle factor involved, one that becomes more significant the farther you travel. When a spacecraft leaves the solar system, it does not merely climb out of the sun's gravitational well. It also acquires a certain velocity relative to the sun and the planets. Over time, this velocity carries it farther and farther away, increasing the energy required to reverse course. Energy in motion grows with the square of speed. That means doubling your speed requires 4 times as much kinetic energy. Tripling it requires 9 times as much. A spacecraft travelling at tens of kilometres per second carries enormous kinetic energy relative to the solar system. and cancelling that energy is not a small task. To slow down by even a few kilometres per second requires a large amount of propellant, burned in engines that must operate reliably after decades in space. To slow down by tens of kilometres per second, the requirements become immense. There is also the matter of timing. If a spacecraft were to turn around immediately after leaving the solar system, the return would be difficult but not impossible in principle. But the longer it travels outward, the farther it must come back, and the more time and energy are required. Distance itself becomes part of the energy debt. Every additional kilometre travelled outward represents additional energy that must be cancelled on the return journey, not only to stop but to match the motion of the solar system again. And the solar system, as we have seen, is not standing still. It moves through the galaxy, and returning to it means not only reversing your own motion, but also matching the motion of a destination that has been travelling through space the entire time you were away. This requirement adds another layer of complexity. It is not enough to head back toward where the solar system once was. You must calculate where it will be when you arrive, adjusting your trajectory and velocity to intercept a moving target after years or decades of travel. Each correction requires fuel. Each manoeuvre adds to the energy cost, and all of that fuel must have been carried from the beginning, because there are no refueling stations in interstellar space. Gravity assists, which helps spacecraft gain speed on the way out, are much harder to use on the way back. To gain a gravity assist, a spacecraft must pass close to a planet in a carefully planned trajectory. But the planets themselves are moving, and aligning a return trajectory to encounter them at the right time and angle becomes increasingly difficult the farther away you start. Even if such alignments were possible, the spacecraft would need to arrive with the correct velocity and direction, which again requires fuel and precise navigation. Another aspect of energy debt comes from the inefficiency of real engines. No propulsion system converts fuel into motion with perfect efficiency. Some energy is lost as heat, some as radiation, some in the imperfect expansion of exhaust gases. Over long missions, these losses accumulate, increasing the total amount of fuel required. And there is also the problem of mass itself. A spacecraft designed for a one-way journey can be relatively light, carrying only the fuel and supplies needed to reach its destination or to operate for a certain period. A spacecraft designed for a round trip must carry everything needed for both legs of the journey, which means more mass, which means more fuel, which means more mass still. This is one of the fundamental reasons why interstellar probes are designed as one-way missions. It is far more efficient to send a small spacecraft outward than to design one capable of returning. The energy required for a round trip grows so large that it quickly becomes impractical with current technology. There is also a quieter, less obvious aspect of energy debt that has to do with time. The longer a journey lasts, the more likely it is that systems will degrade, power sources will decline, and instruments will fail. A spacecraft returning after centuries would need to remain fully functional for far longer than any machine has ever operated continuously. Power sources would need to last, guidance systems would need to remain accurate, and communication equipment would need to function despite radiation and wear. Each of these requirements adds complexity and mass, increasing the energy required for the journey. Time, in this sense, becomes another kind of cost, not measured in fuel, but in reliability and endurance. A mission lasting decades is already challenging. A mission lasting centuries becomes something entirely different, requiring technologies and materials that can endure far beyond current limits. All of these factors combine to create the quiet reality that coming back costs more than leaving, often far more. The outward journey can be assisted by gravity, optimized through careful planning, and carried out with relatively modest fuel reserves. The return journey must overcome not only distance and gravity, but also accumulated velocity, system degradation, and the motion of the solar system itself, and so the balance tips. Leaving becomes possible, returning becomes impractical. This does not mean that returning from all deep space journeys is impossible. Missions within the inner solar system routinely return samples or bring spacecraft back to Earth's vicinity. But as distances grow, the balance shifts. Beyond a certain point, the energy required to come back exceeds what can reasonably be carried or generated. That point is not a sharp boundary. It is a gradual transition, much like the fading edge of the solar system itself. But somewhere beyond the outer planets, beyond the region where gravity assists are readily available and communication delays are manageable, the idea of return begins to slip from the realm of engineering into the realm of speculation. Far from Earth, even within the inner solar system, navigation is already an intricate process. Spacecraft cannot simply look out a window and steer the way a ship at sea once followed coastlines or stars on the horizon. Instead, they rely on careful measurements of radio signals, precise timing, and observations of celestial bodies whose positions are known with extraordinary accuracy. Engineers on Earth track spacecraft by measuring the tiny shifts in the frequency of transmitted signals and by calculating trajectories that account for gravity, motion, and even the subtle pressure of sunlight. As long as a spacecraft remains within the region of the planets, these methods work remarkably well. The sun is bright and unmistakable. Planets serve as reference points. The geometry of the solar system provides a framework, a kind of map in which positions and motions can be calculated with confidence. But as distance increases, that framework begins to fade. The sun, which once filled the sky as a blazing disk, shrinks to a brilliant star among many others. The planets, already faint at great distances, disappear entirely to the naked eye, leaving no obvious markers of direction or distance. The familiar signposts of home recede until the sky looks almost the same in every direction, a field of stars without any clear indication of where you came from or where you're going. This loss of landmarks is not dramatic. Not. It happens gradually, over millions and then billions of kilometers, yet its consequences are profound. Navigation becomes less intuitive, less anchored to visible references, and increasingly dependent on instruments that must function flawlessly over long periods. One method spacecraft use is called celestial navigation, which relies on measuring the positions of stars with extreme precision. By observing how the apparent positions of nearby stars shift slightly against the background of more distant ones, a spacecraft can determine its orientation, and to some extent its location. This technique, known as parallax measurement, is powerful but requires sensitive instruments and careful analysis. Within the solar system, such measurements are aided by the presence of the Sun and planets, which provide bright, well-known reference points. In interstellar space, the process becomes more delicate. The differences in star positions are small, and the accuracy required to determine position over vast distances is extraordinary. Another method involves using pulsars, rapidly rotating neutron stars that emit beams of radio waves or X-rays at extremely regular intervals. Some pulsars are so precise that their pulses rival atomic clocks in stability. By measuring the arrival times of pulses from several pulsars, a spacecraft could, in principle, determine its position in space, much like a GPS receiver on Earth calculates location using signals from satellites. This idea, sometimes called pulsar navigation, is promising, but it depends on sophisticated detectors, stable clocks, and complex calculations. It also requires that the spacecraft maintain a clear view of the relevant pulsars and that its systems remain operational over long periods. Even with such techniques, navigation in interstellar space is not simple. Small errors in measurement or timing can translate into large uncertainties in position. Over years and decades, tiny deviations in trajectory can grow, leading a spacecraft to drift far from its intended path. Within the solar system, these deviations can often be corrected with small course adjustments, using onboard thrusters to nudge the spacecraft back on track. But every correction consumes fuel, and fuel is limited. The farther a spacecraft travels, the more carefully it must conserve its remaining propellant, balancing the need for accuracy against the need to preserve resources. There is also the challenge of orientation. Spacecraft must know not only where they are, but also which way they are pointing. Antennas must be directed toward Earth to transmit data. Instruments must be aimed at targets. Solar panels, when present, must face the sun. Orientation is usually maintained using star trackers, instruments that compare observed star patterns with onboard catalogues. These systems are highly reliable, but they depend on clear views of the sky and functioning electronics. Over long missions, exposure to radiation and the gradual aging of components can degrade performance, making precise orientation more difficult. Communication delays add another layer of complexity. Within the inner solar system, signals take minutes or hours to travel between Earth and a spacecraft. Engineers can monitor data, detect anomalies, and send corrective commands within a reasonable time frame. In interstellar space, those delays stretch into days, months, or even years depending on distance. At such timescales, real-time control becomes impossible. A spacecraft must operate autonomously, detecting and responding to problems on its own. Guidance systems must make decisions without immediate input from Earth, relying on algorithms and programming created decades earlier. Autonomy introduces its own risks. Software errors, unexpected conditions, or gradual degradation of sensors can lead to mistakes that cannot be corrected quickly. Over very long periods, even small uncertainties in navigation can accumulate, causing a spacecraft to drift farther and farther from its intended course. There is also the matter of reference frames. Navigation within the solar system is usually performed relative to the Sun or to Earth. Positions and velocities are calculated in a coordinate system that assumes the Sun as a central reference point. In interstellar space, that reference becomes less meaningful. The spacecraft may need to navigate relative to the galaxy itself, accounting for the motion of stars and the gravitational influences of the Milky Way. This shift in perspective complicates calculations and increases the need for precise measurements. The galaxy is not a static backdrop but a dynamic environment, with stars moving in different directions and at different speeds. Predicting positions over long times requires models that account for these motions, and uncertainties grow as the time horizon extends. Another subtle challenge arises from the very vastness of interstellar space. When distances are measured in light years, even tiny angular errors can correspond to enormous positional uncertainties. A deviation of a fraction of a degree in direction, barely noticeable on a small scale, can result in missing a target by millions or billions of kilometers after years of travel. This is one reason why missions to specific stars, even if propulsion systems capable of such journeys were available, would require extraordinary precision in navigation. The margin for error would be vanishingly small, and course corrections would need to be planned and executed over long periods with great care. All of this contributes to the sense that interstellar navigation is less like following a road, and more like drifting across an ocean without visible shores, guided only by distant lights whose positions change slowly over time. The journey requires patience, precision, and systems capable of functioning reliably for far longer than most machines are designed to operate. There is also a psychological dimension to the idea of navigation without landmarks. Humans have always relied on familiar features of the landscape to orient themselves. Mountains, rivers, coastlines, and stars have served as guides for travellers throughout history. Even in modern cities, people navigate by recognising buildings, streets, and other visual cues. In interstellar space, those cues are absent. The sky looks much the same in every direction, and the distances between objects are so great that movement is imperceptible over short periods. A spacecraft travelling at tens of kilometres per second would still see the stars shifting so slowly that the change would be difficult to detect without precise instruments. This stillness can be deceptive. Motion is constant, but the scale of the universe is so large that change unfolds gradually, almost invisibly. A spacecraft may be travelling millions of kilometres each day, yet the view outside remains nearly unchanged. And this brings us back to the idea of a one-way journey. Navigation without landmarks does not make return impossible in principle, but it makes it far more difficult in practice. The farther a spacecraft travels, the more uncertain its position becomes, the more fuel is required for corrections, and the more challenging it is to align a trajectory that will intersect with a moving solar system after years or decades of travel. Each of these challenges adds to the energy debt we considered earlier, increasing the cost and complexity of any attempt to come back. And as time passes, other factors begin to matter as well, factors that are not immediately obvious but become significant over long durations. There is a quiet difference between short journeys and long ones, a difference that becomes more and more important the farther you travel from the Sun. A spacecraft on its way to Mars may be exposed to the harsh environment of space for months or a few years. A probe heading toward the outer planets must endure for decades. But a vehicle leaving the solar system entirely, drifting into interstellar space, faces something else altogether, an environment where time itself becomes one of the most significant forces acting upon it. Time in space is not an active force in the way gravity or radiation is, yet its effects are relentless. Every material ages, every electronic component slowly degrades. Every protective coating erodes, not suddenly but gradually, in ways that may only become noticeable after years or decades have passed. And in deep space, Far from any possibility of repair or replacement, these slow changes accumulate without interruption. Radiation plays a central role in this process. Within the heliosphere, the sun's magnetic field and solar wind provide a certain level of shielding from the highest energy cosmic rays. It is not perfect protection, but it reduces the intensity of the radiation environment compared with the space between stars. Once a spacecraft crosses that distant boundary, it enters a region where cosmic rays are more abundant and more energetic. These particles are not like the radiation encountered on Earth, where the atmosphere absorbs most high-energy particles before they reach the ground. Cosmic rays can carry energy so high that they pass through shielding and into the materials and electronics of a spacecraft, knocking atoms out of place, creating defects in semiconductors and gradually weakening structures at the microscopic level. At first, these effects may be subtle. A sensor becomes slightly less sensitive. A circuit occasionally produces a transient error. A memory chip develops a fault that must be corrected by onboard systems. Modern spacecraft are designed with redundancy and error-correcting mechanisms to handle such problems, but these solutions are not infinite. Over very long periods, the cumulative damage can exceed the capacity of protective measures. There is also a form of radiation damage that is less obvious, but equally significant. Polymers and insulating materials, which are used extensively in spacecraft construction, can become brittle after prolonged exposure to high-energy particles. Thermal blankets, cable insulation, and seals may crack or lose flexibility, creating vulnerabilities that were not present at launch. Even metals, which seem solid and unchanging, are affected by radiation and temperature extremes. Microscopic changes in crystal structure can alter mechanical properties over time. The effects are slow and often difficult to predict precisely, but they are real, and they become more significant as the years pass. Temperature too plays its part in the slow unravelling of machinery. In deep space, a spacecraft experiences cycles of heating and cooling as it rotates or as its systems operate intermittently. These temperature changes cause materials to expand and contract, creating stresses that can lead to fatigue. Over thousands of cycles, tiny cracks may form, growing gradually until they affect structural integrity or electrical connections. On Earth, machines are maintained and repaired. Parts are replaced, lubrication is renewed, and wear is managed. In deep space, maintenance is impossible. Every component must endure for the entire duration of the mission, and once something fails, it usually remains failed. Power systems are particularly vulnerable to the passage of time. Spacecraft travelling far from the sun rely on radioisotope thermoelectric generators, which convert heat from the decay of radioactive materials into electricity. These devices are remarkably reliable, but they are governed by the laws of physics. The radioactive material decays at a predictable rate, and as it does, the amount of heat produced gradually declines. This means that the electrical power available to the spacecraft decreases year by year. Engineers managing long-duration missions must decide which instruments to turn off in order to conserve power, prioritizing essential systems while allowing others to go silent. Over time, the spacecraft becomes quieter, less capable, and more limited in what it can observe or transmit. Eventually, the power available may no longer be sufficient to operate the communication system. At that point, the spacecraft continues its journey, but it can no longer speak. It becomes a silent traveller, carrying its instruments and records through the darkness without any way to share what it experiences. Communication systems themselves are subject to decay. Antennas, transmitters, and receivers must function reliably despite radiation, temperature extremes, and the gradual aging of electronic components. Signals weaken with distance, requiring higher transmission power or more sensitive receivers. As power declines and systems age, maintaining communication becomes increasingly difficult. Another subtle but important factor is the accuracy of onboard clocks and navigation systems. Over long periods, even tiny drifts in timing or orientation can accumulate, affecting the spacecraft's ability to determine its position or aim its instruments. Correcting these errors requires functioning sensors and control systems, which themselves are subject to wear and degradation. Time also affects the physical environment surrounding the spacecraft. Microscopic impacts from interstellar dust, discussed earlier, slowly erode exposed surfaces. Solar radiation pressure, though weak, can cause slight changes in trajectory over decades. The gravitational influence of passing stars, while usually small, can alter orbits over very long timescales. All of these effects are gradual. None of them, taken alone, is likely to end a mission abruptly. But together, they create a steady decline in capability, a slow unravelling that is as inevitable as the ticking of a clock. This slow decay has profound implications for the idea of a return journey. A spacecraft designed to travel outward for decades can be engineered with the expectation that some systems will fail and that power will decline. But a spacecraft intended to travel outward and then return after centuries would need to remain fully functional for far longer than any machine has ever operated continuously. The longer the journey, the greater the uncertainty. Materials may behave in ways that are not fully predictable over such timescales. Electronics may degrade in unexpected ways. Software, designed and tested on Earth, may encounter conditions that were never anticipated. Even if propulsion systems were capable of providing the energy needed for a return, the spacecraft itself might no longer be capable of making the journey. It might lack the power to operate its engines, the structural integrity to withstand maneuvers, or the functioning sensors needed for navigation. Time, in this sense, becomes a barrier as real as gravity or distance. It is not a wall, but a steady current, carrying everything forward and gradually wearing down even the most carefully designed machines. There is also a broader perspective to consider. Human technology evolves rapidly. The spacecraft we build today are far more capable than those of a few decades ago. A mission lasting centuries would almost certainly outlast the technological context in which it was created. By the time such a spacecraft returned, if it ever did, the civilization that launched it might have changed beyond recognition. This thought adds a philosophical dimension to the idea of one-way journeys. The farther you travel in space, the farther you travel in time as well, not only in terms of the duration of the journey, but in terms of the changes that occur at home while you are away. At the beginning of any space mission, communication feels immediate and reassuring. Signals travel from Earth to a spacecraft in seconds or minutes, depending on distance, and engineers watch streams of data in near real time. Commands are sent, responses are received, and the spacecraft feels like an extension of human presence, a distant but still connected instrument carrying our senses outward. Even journeys to the moon, which lies hundreds of thousands of kilometers away, maintain this sense of closeness. Radio signals take just over a second to make the round trip, a delay so small that it barely interrupts the rhythm of communication. The spacecraft may be far away in physical terms, but in terms of conversation, it is still almost here. As missions venture farther, that rhythm begins to stretch. When a spacecraft is orbiting Mars, the delay can range from several minutes to more than 20 minutes one way, depending on the relative positions of Earth and Mars in their orbits. Conversations are no longer possible. Instructions must be sent and then patiently awaited, and responses arrive long after the question has been asked. Engineers adapt to this. They plan carefully, anticipating problems and programming spacecraft to operate autonomously when immediate guidance is impossible. The delay becomes part of the routine, an accepted feature of deep space exploration. But the farther a spacecraft travels, the more the delay grows. Signals travel at the speed of light, which is incredibly fast, but even light takes time to cross the immense distances of the solar system. A signal from Jupiter takes tens of minutes to reach Earth. From Saturn, more than an hour. From the outermost planets, several hours may pass before a message arrives. And then there are the spacecraft that have travelled beyond the planets, into the outer reaches of the heliosphere and beyond. For them, the delay stretches to many hours, then more than a day for a round trip. A command sent from Earth may not be received until the following day, and the confirmation of its execution may not arrive until the day after that. At this point, communication begins to feel less like conversation and more like correspondence. It is as if letters are being exchanged across a vast ocean, each one taking days to arrive, each reply requiring patience. Distance also weakens the signal itself. Radio waves spread out as they travel, becoming fainter and fainter. By the time a signal from a distant spacecraft reaches Earth, it may be barely distinguishable from background noise, detected only by the most sensitive antennas and the most careful processing. The Deep Space Network, a collection of large radio antennas located around the world, exists in part to handle this challenge. These antennas listen for whispers from the farthest spacecraft, amplifying signals that have travelled billions of kilometres. Even so, there are limits. The farther a spacecraft travels, the more power it must use to transmit, and the more sensitive the receiving equipment must be. But power, as we have seen, is not infinite. Spacecraft rely on onboard power sources that decline slowly over time. Instruments are turned off to conserve energy, and eventually even transmitters may be operated only intermittently, sending brief messages rather than continuous streams of data. At some distance, the signal becomes too weak to detect reliably. Communication ends, not because the spacecraft has stopped working, but because the gulf between it and Earth has grown too great for its fading voice to cross. There is a moment, quiet and almost unnoticed, when the last signal is received. Engineers note the time, analyse the data, and realise that no further messages are likely to arrive. The spacecraft continues on its path, but the connection is gone. From that point onward, it travels alone. This gradual fading of communication has a deeper significance than might appear at first. Communication is not only a technical process, it is also a link between places, a way of maintaining connection across distance. As long as signals are exchanged, a spacecraft remains, in a sense, part of the human world. It sends information, receives instructions, participates in a shared endeavour. When communication ends, that connection becomes symbolic rather than practical. The spacecraft is still there, still moving, but it is no longer part of an ongoing conversation. It becomes more like a message in a bottle, drifting across an ocean without any certainty that it will ever be found. There is also the matter of navigation and control. Within the inner solar system, spacecraft depend on communication with Earth for precise tracking and course corrections. Engineers measure tiny changes in the frequency and timing of radio signals to determine velocity and position with extraordinary accuracy. Commands are sent to adjust trajectories, to aim instruments, to manage systems. Without communication, those adjustments become impossible. A spacecraft must rely entirely on its onboard programming, following a path determined long ago. If unexpected conditions arise, there may be no way to respond. This autonomy is manageable for missions designed to operate in a predictable environment, but over very long periods, uncertainty grows. Tiny deviations in trajectory, once easily corrected, accumulate. The spacecraft drifts, not dramatically, but enough that returning to a specific location becomes increasingly difficult. Communication delay also affects the experience of time itself. For missions lasting decades, the people who designed and launched a spacecraft may retire or pass away before its journey is complete. New generations of engineers take over, learning to operate systems built long before they entered the field. If a mission were to last centuries, the cultural and technological context on Earth might change entirely. Languages evolve, scientific priorities shift, and the meaning of the mission itself may be reinterpreted by those who inherit it. A return journey, if it were possible, would not simply be a physical reunion but a temporal one, bridging vast stretches of time as well as space. The world to which a spacecraft returned might be profoundly different from the one it left. There is another, more subtle aspect of communication delay that is easy to overlook. When signals take years to travel, the idea of real-time awareness disappears. A spacecraft halfway to the nearest star would be sending information about conditions that existed years earlier. By the time the data arrived, those conditions would already be in the past. In a sense, communication across such distances becomes a form of archaeology, a study of events that have already receded into history by the time they are observed. This temporal separation reinforces the sense of distance. The spacecraft is not only far away in space, but also separated in time. Its present inaccessible, its past arriving slowly in fragments of data. All of this contributes to the quiet realization that leaving the solar system is not just a physical departure, but a gradual fading of connection. The farther a spacecraft travels, the longer it takes to speak, the weaker its voice becomes, and the more difficult it is to maintain any meaningful exchange. Eventually, Earth becomes less a place of interaction and more a point of origin, a memory embedded in the spacecraft's records and programming. The signals that once linked it to its creators fall silent, and the journey continues without witness. One of the quiet assumptions behind most journeys on Earth is that resources can be replenished along the way. A car runs low on fuel, and there is a station ahead. An aircraft crosses an ocean, and another airport waits at the far shore. Even ships that once sailed for months carried the expectation that land, supplies, and repair would eventually be found. Travel, in that sense, has always been part of a network, a chain of places where a traveller can pause, recover, and continue. Deep space offers nothing like this. Once a spacecraft leaves Earth, every drop of fuel, every spare component, every watt of energy it will ever use must already be aboard. There are no depots orbiting distant planets, no drifting reservoirs of propellant waiting to be collected, no workshops where damaged systems can be repaired. The farther a spacecraft travels, the more absolute this isolation becomes. It is not merely a matter of inconvenience. The absence of refueling stations changes the nature of the journey itself. It means that decisions made at launch determine the limits of the mission decades later. It means that turning back is not simply a matter of choosing to do so, but of having the means to do so, and those means must have been carried from the beginning. Fuel, as we have seen, is heavy. Carrying enough to accelerate a spacecraft to high speed is already a formidable challenge. Carrying enough to accelerate, decelerate, reverse course, and then decelerate again multiplies that challenge many times over. Each kilogram of fuel needed for the return must be accelerated during departure, which requires still more fuel, and the cycle continues until the requirements become impractical. Within the inner solar system, there are ways to reduce these demands. Spacecraft can use gravity assists, borrowing energy from planets to change speed and direction without expending fuel. They can plan trajectories that take advantage of orbital mechanics, arriving at their destinations with minimal propulsion. But these techniques depend on the presence of massive bodies in predictable orbits, and beyond the region of the planets, such opportunities vanish. Imagine a spacecraft far beyond Neptune, drifting through the scattered outskirts of the solar system. There are no planets nearby, no strong gravitational fields to provide assistance. The spacecraft moves by inertia alone, coasting through darkness. If it wishes to change course or slow down, it must rely entirely on its own engines and whatever propellant remains in its tanks. And those tanks are finite. This finiteness creates a kind of quiet finality. Every maneuver must be weighed carefully, every correction planned with the knowledge that fuel once spent cannot be replaced. Engineers often speak of propellant budgets, careful accounting of how much fuel remains and how it must be used. For long-duration missions, conserving fuel becomes as important as conserving power or protecting instruments. There is also the matter of redundancy. Spacecraft are designed with backup systems to handle failures, but redundancy adds mass, and mass requires more fuel to launch. Every additional component must justify its weight, and there is always a balance between reliability and practicality. A mission cannot carry unlimited spares, and some failures are simply accepted as inevitable. On Earth, repair is a routine part of maintaining complex machines. Parts wear out, seals degrade, electronics fail, and technicians replace or repair them. In deep space, no such intervention is possible. A spacecraft must function with what it has, and when something breaks, the mission must adapt or accept the loss. This reality shapes how missions are designed. Instruments are chosen not only for their scientific value, but also for their durability. Systems are tested to withstand radiation, extreme temperatures, and years of operation. Even so, time and environment take their toll. Components age, lubricants evaporate, and materials slowly change under conditions that cannot be perfectly replicated on Earth. Energy supplies impose another form of limitation. Far from the sun, solar panels become ineffective, and spacecraft rely on power sources that decline gradually over time. As power decreases, instruments are turned off, heaters are reduced, and communication becomes less frequent. The spacecraft continues its journey, but its capabilities shrink, like a traveller shedding possessions to lighten the load. If refueling or resupply were possible, some of these limitations could be managed. A spacecraft could replenish propellant, replace worn components, and restore power systems. But in the emptiness between stars, such infrastructure does not exist, and building it would require an effort far beyond our current capabilities. There have been proposals for future technologies that might change this picture. Some researchers have imagined spacecraft that could collect and use interstellar hydrogen as fuel, using vast magnetic fields to funnel particles into fusion reactors. Others have considered the possibility of constructing fuel depots in space, supplied by materials mined from asteroids or the moons of outer planets. These ideas are intriguing, and they may one day become practical within certain regions of the solar system. But extending such infrastructure into interstellar space would be an undertaking of immense scale, requiring resources and coordination far beyond anything humanity has yet achieved. For now, every spacecraft that leaves the solar system does so with the understanding that it will never refuel, never be repaired, and never return. This understanding is not viewed as a failure or a limitation, but as a design choice, an acceptance of reality. Missions like Voyager were conceived from the beginning as one-way journeys. Their purpose was to explore, to gather data, and to continue outward as far as their systems allowed. The idea of bringing them back was never part of the plan, because the cost and complexity would have been overwhelming. There is something quietly poetic about that decision, though not in a dramatic or sentimental sense. It reflects a practical recognition that some journeys are meant to be outward, that exploration sometimes means letting go rather than returning. The absence of refueling stations also affects how we think about human travel beyond the solar system. A crewed spacecraft would require not only propulsion and fuel, but also food, water, air, and protection from radiation for years or decades. Recycling systems could extend supplies, but they would need to operate flawlessly for the entire duration of the mission. Any failure in life support systems would be critical, and without the possibility of resupply, there would be little margin for error. Even if propulsion technology advanced to the point where interstellar travel became feasible, the challenge of sustaining human life for such journeys would remain formidable. A return trip would double those requirements, increasing the mass and complexity of the spacecraft and making the mission even more demanding. This is why many serious proposals for interstellar exploration focus on robotic probes rather than human crews. Machines can endure conditions that would be intolerable for people, and they do not require air, food, or protection from psychological isolation. Even so, the limits of fuel, power, and reliability still apply. There is also a deeper perspective to consider, one that emerges when thinking about time as well as distance. A spacecraft travelling for centuries or millennia becomes, in a sense, detached from the civilization that launched it. Languages change, cultures evolve, and scientific priorities shift. The world that built the spacecraft may no longer exist in the same form by the time it reaches its destination, let alone if it were to attempt to return. In that sense, the absence of refueling stations is not only a practical limitation, but also a symbol of the separation that occurs during such journeys. The farther a spacecraft travels, the more it becomes a relic of its origin, carrying with it a snapshot of a particular moment in human history. Imagine again that small spacecraft drifting outward, its engines long silent, its tanks nearly empty, its systems operating on diminishing power. It has everything it will ever have, nothing more, nothing less. Every manoeuvre, every transmission, every observation must be made within the limits set at the moment of launch. There is a quiet discipline in that constraint. It requires careful planning, precise execution, and a willingness to accept that some possibilities must be left behind. The spacecraft cannot turn back simply because it wishes to. It cannot seek shelter or replenishment. It can only continue forward, following the trajectory determined by physics and the decisions made long ago. And as it continues, the distance between it and the solar system grows not only in kilometres, but in opportunity. The chance to refuel, to repair, to return, fades steadily until it becomes so remote that it is no longer considered at all. There is another factor that quietly shapes the possibility of leaving the solar system and coming back, and it is not a limitation of fuel or machinery, nor a hazard of radiation or distance. It is woven into the structure of the universe itself. Time does not pass in exactly the same way for everything, and when motion becomes fast enough and distance is large enough, the differences begin to matter. In everyday life, time feels steady and uniform. A second is a second, whether you are walking, sitting, or riding in a car. Clocks tick at the same rate, and the passage of minutes and hours feels consistent enough that we rarely question it. This constancy is so familiar that it seems like an unquestionable feature of reality. but physics has revealed that time is more flexible than our senses suggest. The faster an object moves, the more slowly time passes for it, relative to something at rest. This effect, known as time dilation, becomes noticeable only at very high speeds approaching a significant fraction of the speed of light. At the velocities of everyday travel, the difference is far too small to detect without extremely precise instruments. Yet even though the effect is tiny at low speeds, it is real, and it has been measured many times. Atomic clocks carried on fast aircraft or satellites run slightly slower than identical clocks on the ground. The global positioning system must account for these differences, adjusting satellite clocks so that navigation remains accurate. Without corrections for relativity, GPS would quickly become unreliable. In the context of leaving the solar system, these effects are usually small, because current spacecraft travel far below relativistic speeds. Voyager 1, for example, moves at about 17 kilometers per second relative to the Sun, which is only a tiny fraction of the speed of light. At that speed, time dilation is negligible. But when we consider the idea of travelling far beyond the solar system, especially journeys to nearby stars that might require much higher velocities, relativity begins to play a more significant role. And even before reaching those extreme speeds, time itself becomes an important factor in another way, not because it flows differently, but because so much of it passes during the journey. A spacecraft travelling outward for decades or centuries experiences time in a straightforward way. Its onboard clocks tick normally, its systems age normally, and its journey unfolds moment by moment. But the world it left behind is also moving forward in time, changing, evolving and transforming in ways that cannot be reversed. This creates a kind of separation that goes beyond distance. Even if a spacecraft could return physically, it could not return to the same moment in history. The Earth it left would no longer exist in the same state. People would have aged or passed away, cities might have changed, entire cultures might have evolved in ways that would feel unfamiliar. This effect is not dramatic or sudden, but it is relentless. Time moves in one direction, and every journey outward carries you further not only in space, but also in time. Relativity deepens this separation when speeds become higher. If a spacecraft were able to travel at a significant fraction of the speed of light, time aboard the spacecraft would pass more slowly than on Earth. This is not science fiction, but a well-tested consequence of Einstein's theory of special relativity. Imagine, for example, a spacecraft travelling at half the speed of light to a distant destination. From the perspective of observers on Earth, the journey might take many years, but for the travellers aboard the spacecraft, less time would pass. Their clocks would run more slowly relative to those on Earth. At even higher speeds, the effect becomes more pronounced. A journey that takes decades on Earth might feel like only a few years to those on board. This might sound like an advantage, a way of making long journeys more manageable. But relativity introduces a complication when it comes to returning. The faster you travel, the greater the difference in elapsed time between you and the place you left. A round trip at relativistic speeds could mean that travellers return to an Earth that has aged far more than they have, perhaps by centuries. This scenario is sometimes illustrated by the so-called twin paradox, in which one twin travels at high speed while the other remains on Earth. When the traveller returns, less time has passed for them than for the twin who stayed behind. The effect is not paradoxical in a physical sense, but it does challenge our everyday intuition about time. In the context of interstellar travel, this means that even if a return journey were physically possible, it would not be a return to the same time. The travellers would arrive in a future that has moved far beyond the era in which they departed. There is another way in which time works against return, one that does not require relativistic speeds at all. It has to do with the accumulation of delays in communication, planning, and execution over long distances. A spacecraft travelling far from the solar system must operate increasingly independently. As communication delays grow longer and longer, decisions that once could be guided from Earth must be made on board. Navigational adjustments must be planned in advance. Opportunities for correction become fewer and farther between. Time, in this sense, becomes an obstacle, because it stretches the interval between cause and effect. A problem detected today may not be addressed until weeks or months later, depending on distance and communication schedules. By then, the spacecraft may have drifted far from its intended path, and correcting the deviation may require more fuel than is available. Even the act of turning around takes time. A spacecraft cannot simply reverse direction instantly. It must reorient itself, fire its engines, and gradually alter its trajectory. Each maneuver consumes time and resources, and the longer the journey has continued, the more time and energy are required to undo it. There is also the matter of orbital mechanics. The solar system is not a fixed target waiting to be rejoined. The planets move in their orbits, and the entire system moves through the galaxy. A spacecraft attempting to return after many years would need to calculate not where Earth was when it left, but where Earth will be when it arrives. This prediction becomes more difficult the farther into the future one tries to look. Small uncertainties in position and velocity grow over time, and the cumulative effects of gravitational interactions can alter trajectories in subtle ways. Navigating across such distances requires extraordinary precision and planning, and even then, success is not guaranteed. Relativity also affects navigation in more subtle ways. At high speeds, the apparent positions of stars shift due to a phenomenon known as aberration, in which the direction of incoming light is altered by the motion of the observer. A spacecraft travelling at relativistic speeds would see the sky distorted, with stars appearing to crowd toward the direction of travel. This effect complicates the use of stars as navigational references and requires adjustments in measurement and calculation. Instruments must account for these distortions to determine accurate positions and orientations. There is also the challenge of synchronizing clocks. Accurate navigation depends on precise timing, and when time itself flows at slightly different rates in different reference frames, keeping clocks synchronized becomes more complex. Signals exchanged between Earth and a fast-moving spacecraft would experience shifts in frequency and timing that must be carefully corrected. All of these effects add layers of difficulty to any attempt at a round trip over interstellar distances. They do not make return impossible in principle, but they increase the complexity and the cost, both in energy and in planning. And beyond the technical challenges lies a quieter, more human realization. Time is not something that can be stored or replenished like fuel. Every year spent travelling outward is a year that cannot be recovered. Even if a spacecraft could return physically, it would return to a different world, separated from its point of origin by an unbridgeable gap in time. This realization changes how we think about journeys. On Earth, returning home usually means returning to a place that is still recognizable, still connected to the memories of departure. In deep space, the concept of home becomes more abstract. It is not only a location, but a moment in history, and that moment recedes farther into the past with every passing day. If you imagine again that small spacecraft drifting outward, you can picture not only the distance growing, but the years accumulating, one after another, silent and unhurried. Its clocks tick steadily, its systems age, and the world it left behind moves forward in time, changing in ways that cannot be reversed. Eventually, the separation becomes more than physical. It becomes temporal, a gap measured not only in kilometres but in decades, centuries, perhaps even longer. Long before the first spacecraft ever left Earth, long before rockets and radio signals and trajectories were calculated on glowing screens, there was already an awareness in human experience of what it means to go somewhere from which return is unlikely. Sailors once crossed oceans knowing that some ships never came back. Explorers walked into deserts and polar regions carrying the quiet understanding that distance and isolation could become permanent. Even migrations throughout history often meant leaving behind familiar landscapes and accepting that the place called home would never again be seen. Yet leaving the solar system carries a different kind of weight, one that is not only physical but psychological. It is not simply travelling far away. It is departing from the shared environment in which every human life has unfolded, the sun that has risen over every civilization, the sky that has framed every story, every memory, every moment of history. That realization does not arrive all at once. It grows gradually, much like distance itself. At first, leaving Earth might feel like an extension of journeys already made. Astronauts orbiting the planet still see continents, oceans and clouds passing beneath them. They watch sunrises sweep across the horizon in minutes instead of hours. Earth remains close, visually and emotionally, a constant presence filling the sky. Travelling to the moon changes that perspective, but only slightly. The Earth becomes a sphere suspended in darkness, small enough to fit within a window, yet still unmistakably detailed. Oceans and weather systems are visible. The colours of land and water remain familiar. Communication is still possible in near real time. The sense of connection persists. But as distance increases, something subtle begins to change. The Earth shrinks, first to the size of a coin held at arm's length, then to a bright star among many others. Details vanish. The continents and oceans disappear into a single point of light, and eventually even that point becomes difficult to distinguish from the background of stars without instruments. At that stage, the visual connection to home is gone. Earth is no longer a place you can see. It becomes an idea, a memory, something known intellectually but no longer experienced directly. This shift has a psychological dimension that is difficult to measure but easy to imagine. Human beings evolved in a world of immediate surroundings, where the horizon was rarely more than a few kilometers away, where the sky and land provided constant reference points. Even in modern cities, the environment remains filled with familiar cues, buildings, streets, trees, the sound of wind, the presence of other people. Deep space offers none of these things. There is no horizon, no weather, no sound, no sense of movement except what instruments report. The view outside changes so slowly that days or weeks may pass without any noticeable difference. Stars remain fixed in their patterns, and the darkness between them feels endless. For a robotic spacecraft, this environment is simply a set of conditions to be endured. For a human being, it would be something else entirely, an experience of isolation deeper than anything encountered on Earth. Isolation is not only the absence of other people, it is also the absence of shared context, the feeling of being removed from the rhythms and events that shape everyday life. News, conversations, the passing of seasons, the subtle changes of light and weather, all of these form the background of human experience. In deep space, that background disappears. Communication delays, as we have already considered, add to this separation. Messages take longer and longer to arrive, and replies take longer still. Conversations become exchanges of recorded thoughts rather than real-time dialogue. The sense of immediacy fades, replaced by a kind of quiet distance that grows with every passing day. There is also the awareness that help is not coming. On Earth, even in remote regions, there is usually some possibility of rescue or support. A stranded ship can send a distress signal. An aircraft in trouble can call for assistance. Even in the most isolated environments, there remains a sense that the wider world is still within reach. In deep space, that sense disappears. A spacecraft millions or billions of kilometers from Earth is entirely on its own. Any problem must be solved with the resources available on board, and some problems cannot be solved at all. This knowledge changes how one thinks about risk and safety. It creates a different relationship with uncertainty, one that requires acceptance rather than expectation of intervention. Another psychological aspect of leaving the solar system is the gradual fading of shared time. On Earth, people live within a common temporal framework. Days and nights follow the same rhythm. Holidays, events, and cultural moments occur simultaneously for millions of people. Even those living far apart remain connected by a shared calendar and a shared sense of time passing. Far from Earth, that shared rhythm disappears. A spacecraft does not experience sunrise and sunset in the same way. Its internal clocks may mark the passage of hours and days, but those markers are arbitrary, disconnected from the natural cycles that have shaped human perception of time for thousands of years. Over long journeys, this disconnection could become profound. The passage of time would be measured not by seasons or changing light, but by the quiet ticking of instruments, by scheduled system checks, by the slow progression of a mission timeline that stretches far into the future. There is also the awareness that the world left behind continues to change. People age, societies evolve, discoveries are made, and history moves forward. The farther one travels, the greater the gap between the traveller's experience and the life unfolding on Earth. This gap is not only physical but emotional. Relationships, memories, and cultural references gradually lose their immediacy. The traveller becomes, in a sense, a visitor from another time, carrying with them a snapshot of the past while the present moves on without them. In the case of robotic spacecraft, this separation is symbolic rather than personal. But even then, there is a human tendency to project meaning onto these machines, to see them as emissaries carrying a part of our civilization into the darkness. When a spacecraft like Voyager sends back its final signal, there is often a quiet sense of farewell, not because the machine itself feels anything, but because it represents a connection that has ended. The idea of a one-way door captures this feeling well. A door that closes behind you is not merely a physical barrier. It marks a transition, a point beyond which returning becomes increasingly difficult, then impractical, and finally impossible. Leaving the solar system is such a transition. At first, the door is still open. Turning back would be possible, though costly. A little farther on, it becomes harder. Eventually, the distance, the energy required, and the passage of time combine to close the door entirely. What makes this psychologically significant is the awareness of that closure. Knowing that a journey is one way changes how it is experienced. Each kilometre travelled outward is not only a step into new territory, but also a step away from everything familiar. There's also a broader perspective to consider. Humanity as a whole has always lived under the same sun, within the same gravitational domain, surrounded by the same planets and stars. Leaving the solar system would mean becoming, in a literal sense, separate from that shared environment. It would be like leaving not just a country or a planet, but an entire chapter of existence, stepping into a new context where the reference points of human history no longer apply. This does not mean that such journeys are undesirable or futile. Exploration has always involved leaving familiar boundaries behind, but it does mean that the psychological dimension of interstellar travel is as real as the physical one. Understanding this helps explain why missions that leave the solar system are often framed not as round trips, but as voyages of discovery, outward journeys that accept the finality of distance rather than attempting to overcome it. Long before any spacecraft crossed the boundary of the heliosphere, long before the faint whisper of a signal arrived from beyond the outer planets, there was a moment when a small group of people sat together and thought about the future in a very unusual way. They were not thinking about years or decades. They were thinking about thousands of years, perhaps millions, about the possibility that something built by human hands might outlast the civilizations that created it and continue drifting through the galaxy long after its makers were gone. That thought led to a remarkable decision. If a spacecraft was going to leave the solar system and never return, then perhaps it should carry something more than instruments and transmitters. Perhaps it should carry a message. The spacecraft that would bear this message were the Voyager probes, launched in 1977, at a time when much of modern computing was still in its infancy, when the internet did not yet exist, and when the idea of reaching interstellar space was still largely theoretical. These spacecraft were designed to explore the outer planets, to send back images and measurements that would deepen our understanding of the solar system. But from the beginning, there was also an awareness that their journeys would not end there. After completing their planetary encounters, they would continue outward, following trajectories that would carry them beyond the sun's gravitational domain. And so the question arose, if these spacecraft would travel for tens of thousands of years, perhaps longer than any human structure had ever endured, what should they carry with them? The answer took the form of a golden record, a phonograph record plated in gold carefully mounted aboard each Voyager spacecraft. It was a simple object in some ways, a circular disc with grooves that could be played with a stylus, much like the vinyl records that were common at the time, but its contents were anything but simple. The record contained sounds and images intended to represent the diversity of life and culture on Earth. There were greetings spoken in many languages, from widely spoken tongues to those known by only small communities. There were recordings of natural sounds, wind, thunder, waves, birds, and the rhythmic beating of a human heart. There was music, a selection that ranged across cultures and centuries, from classical compositions to traditional songs and modern pieces. There were also images encoded in analogue form, pictures of landscapes, animals, plants, and people, along with diagrams explaining basic scientific concepts and the structure of DNA. Even the location of the solar system was included, encoded in a way that might be understood by any civilization capable of finding and examining the record. What is striking about this effort is not only the care that went into selecting the contents, but also the understanding that the record was unlikely ever to be found. The vastness of interstellar space makes encounters between objects exceedingly rare. The Voyager spacecraft are tiny, far smaller than a grain of sand on the scale of the galaxy, and the probability that they will be discovered by another civilization is extremely small. And yet the record was created anyway. There is something deeply human in that gesture, the desire to leave a trace, to send a greeting into the unknown even when the chances of reply are almost non-existent. It reflects a kind of quiet optimism, not the expectation that someone will answer, but the belief that the act of reaching out has value in itself. The creation of the golden record also reveals an awareness of the one-way nature of the journey. No one planned to retrieve it. No one expected the Voyagers to return. From the moment they were launched, it was understood that they would travel outward until their power supplies failed and their signals faded into silence. In that sense, the record is not only a message to hypothetical distant listeners, but also a message to the future, a reminder of what humanity was like at a particular moment in history. It is a snapshot of a world in the late 20th century, preserved in metal and carried into the darkness. The spacecraft themselves are remarkable examples of engineering designed for longevity. Their systems were built with redundancy and durability in mind, capable of operating for far longer than originally planned. Even so, their designers knew that time would eventually take its toll, power would decline, instruments would fail, and communication would cease. And yet the Voyagers continue to function, decades after their launch, travelling farther from the Sun with each passing year. Their signals, faint but still detectable, carry data from regions of space that no spacecraft had ever explored before. Each transmission is a reminder of how far they have travelled and how long they have endured. There is a certain stillness in imagining their journey now. They are no longer visiting planets or sending back dramatic images of swirling clouds and icy moons. They are moving through a region where changes are subtle, measured in particles and fields rather than landscapes and storms. The pace of discovery has slowed, but the significance of their journey has only grown. Because the Voyagers are not merely spacecraft anymore. They are the first objects built by humans to enter interstellar space, the first to leave the Sun's immediate neighbourhood and continue onward into the vastness between stars. And they are doing so without any possibility of return. This fact was never seen as a failure or a limitation. It was simply accepted as part of the mission. The goal was to go, to observe, to transmit, and then to continue outward as long as possible. Return was never part of the equation. That acceptance reflects a broader truth about exploration. Not every journey is meant to be retraced. Some paths lead outward, carrying travellers into regions where the cost of coming back would be greater than any benefit. In such cases, the value lies in the journey itself, in what is learned and what is shared along the way. The golden record embodies this idea. It is not a tool for return, but a companion for the journey, a symbol of the civilization that built the spacecraft and sent it on its way. It carries voices and music, images and ideas, fragments of a world that remains vibrant and alive even as the spacecraft drifts farther away. There is also something quietly profound about the materials chosen for the record. Gold was selected not for its beauty, but for its resistance to corrosion and chemical change. In the vacuum of space, shielded from the worst effects of radiation by its protective cover, the record could remain intact for millions of years. This means that long after the Voyagers have fallen silent, long after their electronics have ceased to function, the records may still exist, circling the galaxy in slow, patient orbits. They may never be found, but they will endure, silent witnesses to a moment in human history. Thinking about this can change the way one sees the night sky. Among the countless stars, there are now two small objects, each carrying a tiny archive of Earth, moving steadily outward. They are unimaginably far away, and yet they remain part of our story, threads extending from our present into a distant future. Their journey also reminds us that leaving the solar system is not only a theoretical concept, it has already happened. Human-made objects are already travelling beyond the Sun's distant frontier, following paths that will never bring them back. And that realisation brings us gently to another question. If the one-way nature of these journeys is so well understood, why are missions designed this way from the beginning? Why do engineers and scientists plan outward trajectories without considering return, even in theory? It might seem at first that the reason we do not plan return missions from beyond the solar system is simply caution, or perhaps a lack of ambition. It is easy to imagine that somewhere in the future, when technology improves, spacecraft will travel outward and then come home again, much like explorers once crossed oceans and later retraced their routes. The absence of such plans today can appear, on the surface, like a temporary limitation rather than something more fundamental. But when engineers and physicists speak about journeys beyond the solar system, the conversation rarely turns to return missions, and the reason for that is not fear or pessimism. It is physics, the quiet, consistent set of rules that governs motion, energy, and the behaviour of matter. These rules are not barriers placed in our way. They are simply the conditions of the universe we inhabit. And when those conditions are examined carefully, the idea of a comeback begins to look less like a technical challenge and more like a problem that grows exponentially with every kilometre travelled outward. One of the first realities to consider is the sheer amount of energy required to change velocity in space. Acceleration and deceleration are not opposites in the sense that one cancels the other without cost. Each requires fuel, and fuel has mass. Carrying fuel to slow down later means carrying extra mass during departure, which in turn requires more fuel to accelerate in the first place. The relationship grows quickly, and what begins as a manageable requirement can become overwhelming. This is not a matter of engineering skill or clever design alone. It is built into the mathematics of rocket propulsion. Even with highly efficient engines, the amount of propellant required to perform large velocity changes increases rapidly as mission requirements grow. For journeys that extend far beyond the planets, the amount of fuel needed for a return becomes so large that launching it from Earth would be extraordinarily difficult. There is also the matter of timing and alignment. Within the solar system, return missions are often planned around orbital mechanics, taking advantage of planetary positions that minimise the energy required. A spacecraft travelling to Mars, for example, may wait for months or years until Earth and Mars are aligned in a way that allows a relatively efficient transfer. But beyond the outer planets, these opportunities diminish. There are no large bodies to provide gravity assists, no predictable alignments that significantly reduce the energy needed to reverse course. A spacecraft travelling through interstellar space would have to rely entirely on its own propulsion to slow down, turn around, and accelerate again. Each of those steps consumes energy, and each requires systems that remain fully functional over very long periods. Engines must ignite reliably after decades or centuries, fuel must remain stable, guidance systems must remain accurate. These are not impossible requirements in principle, but they become increasingly demanding as mission durations extend. Another factor often overlooked is the cumulative effect of small uncertainties. Navigating across billions of kilometres already requires extraordinary precision. Over interstellar distances, even tiny deviations in trajectory can grow into enormous differences in position. Correcting those deviations requires fuel, and fuel, as always, is limited. Returning to a moving target adds further complexity. The solar system does not remain in one place while a spacecraft travels outward. It continues its orbit around the galaxy, and the planets continue their orbits around the Sun. A spacecraft attempting to return after many years would need to predict not where Earth was when it left, but where Earth will be when it arrives, adjusting its path accordingly. Predicting planetary positions decades or centuries into the future is possible with high accuracy, but it requires careful calculations and continuous monitoring. Any errors in trajectory would need to be corrected, again consuming fuel and reducing the margin for success. The environment of deep space also plays a role in shaping mission plans. Radiation, micrometeoroid impacts, and the gradual aging of materials all affect spacecraft over time. Systems designed to operate for decades may not remain reliable for centuries. Power sources decline, electronics degrade, and structural components experience slow but persistent wear. Designing a spacecraft capable of making a round trip beyond the solar system would mean designing systems that can endure not only the outward journey, but also the return, doubling or tripling the required lifespan. Each additional year increases the likelihood of failure, and redundancy adds mass, which in turn increases fuel requirements. Communication delays introduce another challenge. A spacecraft travelling far from Earth must operate autonomously, making decisions without real-time input. For a return mission, this autonomy would need to extend over very long periods, handling unexpected situations that engineers on Earth could not anticipate. The farther the spacecraft travels, the longer the communication delays become, and the more difficult it is to maintain precise control. Commands sent from Earth might take years to arrive, and responses years more to return. This makes coordinated operations increasingly impractical, especially for complex maneuvers required to reverse course and navigate back through the solar system. There is also a more subtle aspect of physics that shapes how missions are planned, and it has to do with efficiency. When a spacecraft leaves the solar system, it can take advantage of the motion of Earth and the gravity of planets to gain speed with relatively little fuel. These opportunities are like stepping stones, each providing a boost that reduces the amount of propellant needed. On the return journey, those stepping stones are not always available. The spacecraft may approach the solar system from a direction that does not allow efficient gravity assists, or the timing of planetary positions may not align with its arrival. Without those assists, the amount of fuel required increases significantly. Even if advanced propulsion systems become available, the basic relationship between energy and velocity remains. Slowing down from high speed requires removing kinetic energy, and that energy must go somewhere, usually into exhaust expelled in the opposite direction. The faster you travel, the more energy must be dissipated, and the more propellant is needed. This is why many serious proposals for interstellar probes focus on one-way missions. It is far more practical to design a spacecraft that accelerates once and then coasts indefinitely than to design one capable of reversing course after travelling vast distances. There's also a philosophical dimension to this, though it arises naturally from practical considerations. Exploration does not always require return. Many of the most important discoveries in science have come from instruments and experiments that were never intended to come back. From deep-sea probes, to weather balloons, to spacecraft sent to distant planets, the value of a mission lies in what it learns and what it reveals, not necessarily in bringing the spacecraft home. Data transmitted across billions of kilometers can be far more valuable than the physical return of a machine. This perspective shapes how missions are conceived. Engineers and scientists focus on maximizing the scientific return during the time when communication is possible, knowing that eventually the spacecraft will fall silent. The journey beyond that point is not seen as wasted, but as a continuation of exploration, even if no further data can be received. Another reason why comeback missions are not planned is that technology itself evolves. A spacecraft launched today may be overtaken in capability by one launched decades later. This is sometimes called the incessant obsolescence problem in interstellar mission planning. A probe travelling for centuries might be surpassed by faster or more advanced probes sent later, making a return less meaningful from a scientific perspective. In this sense, exploration becomes a relay rather than a single journey. Each generation of spacecraft extends our reach a little farther, building on the achievements of those that came before. Return is less important than continuity. Reflecting on all of this reveals that the absence of planned comebacks is not due to a lack of courage or imagination. It is a recognition of the realities imposed by distance, energy, time, and the environment of space. These factors combine in ways that make round trips beyond the solar system extraordinarily difficult, while one-way missions remain achievable and scientifically valuable. There is something about the idea of leaving forever that feels distant at first, almost abstract, the kind of thought that drifts through the mind without settling. After all, most journeys in life are temporary. Even long separations usually end in reunion. Travellers return home, ships come back to harbour, and the familiar rhythms of departure and arrival repeat again and again. But the farther one looks into space, the more that rhythm begins to change. Distance stretches, time expands, and eventually the idea of return fades, not dramatically, not suddenly, but gradually, the way a shoreline disappears into haze as a ship moves farther out to sea. Leaving the solar system is like that. There is no single moment when someone announces that return is no longer possible. Instead, there is a slow accumulation of realities: gravity, energy, distance, time, the aging of machines, the fading of signals, all of them quietly adding weight to the same conclusion. A spacecraft drifts outward, and with every passing year, the path behind it becomes harder to retrace. And yet, there is nothing tragic in this. It is simply the nature of the journey. If you imagine standing on Earth at night and looking up at the stars, it is easy to feel that space is silent and empty, a distant backdrop to everyday life. But in truth, even now, there are human-made objects moving through that darkness, small and faint, travelling farther from the sun than any explorers in history. They are not racing or struggling. They are simply moving, carried by inertia, following trajectories that will continue long after their creators are gone. Those spacecraft do not experience departure the way we do. They do not feel distance or time. But for us, thinking about them invites reflection, not only on physics and engineering, but on the meaning of exploration itself. Because leaving forever is not only about distance, it is also about perspective. From within the solar system, everything feels connected. The sun rises and sets, the moon changes its shape, planets drift slowly across the sky. Even if we never travel beyond Earth, we are part of this larger system, sharing the same star, the same gravitational dance, the same slow movement through the galaxy. To leave that system is to step outside a shared story. It is to move into a region where the sun becomes just another star, where the familiar patterns of the night sky begin to shift, where the connection to home becomes something remembered rather than experienced. That thought can feel unsettling at first, but it can also be peaceful. The universe is vast and movement through it is natural. Stars themselves drift, galaxies collide and merge, and even the atoms in our bodies were forged in places far from here, carried across unimaginable distances before becoming part of the world we know. In that sense, leaving is not an exception, but a continuation of a much older story, one that began long before Earth formed, when clouds of gas and dust moved through space and gradually came together to form stars and planets. The difference, perhaps, is that now we're aware of the journey. Awareness changes how we think about distance and time. A spacecraft drifting beyond the solar system is not only an object in motion, it is a reminder of how far curiosity can carry us, of how questions asked on a small planet can lead to journeys that span billions of kilometres. And yet, even as those journeys extend outward, the meaning of home becomes clearer rather than less important. Home is not merely a location in space. It is a network of relationships, of shared experiences, of memories and stories. It is the place where time is measured in familiar ways, where voices are heard without delay, where the sky and the ground and the air form a continuous living environment. A spacecraft leaving the solar system carries none of those things with it, only records and instruments, and silent metal structures built to endure. It moves through regions where there is no weather, no sound, no changing seasons, only the steady passage of time and the faint glow of distant stars. That contrast highlights something essential about exploration. The farther we look outward, the more we understand the rarity and fragility of the place we come from. Earth is not merely a point in space. It is a world of oceans and clouds, of forests and deserts, of countless forms of life sharing a thin layer of air warmed by a single star. Seen from afar, it is small, almost fragile, yet it contains everything we have ever known. Leaving that world, even in imagination, brings a new appreciation of its uniqueness. There is also a quieter realization that emerges when thinking about journeys without return. Not every path in life is meant to circle back. Some experiences once lived remain in the past. Some moments once gone cannot be revisited except in memory. This is not something to regret. It is simply the nature of time. In a way, every day is a one-way journey. Each sunrise leads to a sunset that will never be repeated in exactly the same way. Each year carries us forward, never backward.